My name is Nikhil and I work as an assistant professor in the Department of Mechanical Engineering at Malviya National Institute of Technology, Jaipur. It is about 200 to 50 kilometers from here. And today I will present two aspects. One is spray characterization for renewable fuels, and the second one is particulate emission characterization for renewable fuels. The fuels which have been selected for this investigation is 15% volume by volume blend of primary alcohols, ethanol, methanol and butanol with gasoline. Gasoline would be the baseline fuel. BU here stands for butanol and E is ethanol, M is methanol. So these experiments have been done in gasoline direct injection engine. So the flow of the presentation would be to understand the behavior starting from of these fuels, starting from spray characterization in an ambient condition, and then obtaining the results such as macroscopic and microscopic investigation. So as in we will have an optical constant volume spray chamber which is unpressurized, and we try to look at the macroscopic and microscopic spray investigation, and then with some understanding from those results we move to an optical engine with pressurized condition and try to compare what is the difference in the droplet size or the droplet velocity with respect to the fuels. And we did not do any experiment with compressed chamber because the condition which the constant volume spray chamber which is pressurized, because that may involve some actual errors when we compare with the ambient condition result. So we wanted to do with the actual engine. And then second part is related to particulate emission characterization. So I will touch very little about this particulate emission characterization. So in this we used catalytic stripper to strip off the particles to follow this, or the thermal denuder to as per the PMP protocol, and characterize renewable fuel both with the diesel engine for the diesel fuel and gasoline. And the instrument used for this particulate emission is SMPS and DMS 500 with this. So with this I will now directly, I will not have any introduction and move to the results section directly. In this we can see that the droplet, when it comes into the combustion chamber, it has to experience high temperature, high pressure conditions, and the droplet size and the velocity changes directly due to many phenomena that occurs inside the combustion chamber. So with this, the two experiment setup have been used. One is constant volume spray chamber, unpressurized one. In this we used high speed camera and to capture the images, and there is NI card to initiate the injection, and we have air driven liquid pump which is used to compress the gasoline, and the pressure used is of the low gasoline direct injection pressure is used in this case. And on the other side is the engine setup, which is gasoline direct injection engine, and it is coupled with a transient dynamometer and ECU interface, open ECU. In this we can vary the fuel injection timing, amount of the fuel that has to be injected, and pressure of the fuel that has to be injected, and also we can vary the spark timing. We can advance or retard the spark timing. So this is the overall conditions, and lower side you can see some of the metrics that on certain condition the experiments were done, and on certain condition the experiments were not done. So we can see the fuel injection pressure is low, 40 bar, 80 bar, 120 bar and 160 bar for the gasoline direct injection engine. The limitation for lower fuel injection pressure is due to this air driven liquid pump. And these are some of the images. So these, on the left side we see that it is at one constant fuel injection pressure of 120 bar, and on the other side the fuel injection pressure is varying, but the fuel is fixed. So 4 fuels and 1 pressure, on that side 1 fuel and 4 pressure. So in this, these images is from the constant volume spray chamber, and we are trying to understand macroscopic macroscopic characterization of the fuel. So we don't get much of the information, but we can see what is the spray cone angle, or what is the, how the air interacts with the different fuels, and when, what is the we can say how does the air is trapped inside the different tubes. So here we see on that side I have picked one of the image on the right side and tried to depict the what we can get from these macroscopic investigations. So for example, let us go from the right side, void created by the airflow. So we have certain voids because of the nature of the because of the distance that is within the injector. Then vaporization happens towards the end, and then undistinguished fumes are there on the lower side, and also the fuel is pushed towards the different direction from the periphery. So all this understanding we can get from these images, but still this macroscopic investigation we do not extract anything great, because we are comparing the lower blends of the fuel. And this is certain on which the this is 6-hole injector, and the downstream distance from the injector is 40 mm. And also we have these directions, like when I talk about velocity, Vx, Vy, Vz, and those are the coordinates. And all the results from the phase Doppler interferometry would be illustrated in terms of head and tail of the sections. Yeah, so this is macroscopic investigation: spray cone angle, spray penetration length, and that is the in cylinder pressure for the different spark timing. So we can see that the spray cone angle, it is decreasing as the time of injection is increasing, and also spray penetration length, there is not much difference because the blends are in the lower side. And this is the so with this understanding, having some understanding from the ambient condition and gathering some information, now we move to the optical engine, and we skip in between the pressurized chamber to measure the droplet side and velocity. So now we go to the optical engine results. So this is the lower side is the optical engine, and upper side is the schematic from the top view when we look at these let us say the probe volume. So probe volume is on the center of the optical window, you can see, and it is little bit challenging to have a probe volume accurately because of the inherent nature of the optical window. It will have certain thickness, and also it will have certain curvature. So the laser, when it passes from the thick medium, so it will experience different kinds of refraction and reflection. So how did we calibrate this? Is we took this optical window out of the engine and kept it on the top here, and calibrated that for the amount of diffraction that we will experience. And then we moved with the help of the drivers, we moved the drivers down, and then we believe that this is going to be the same. The position of the probe volume would be same even after the reflection and diffraction. And the extra window, there was one more optical window that helped us to achieve this probe volume. So we can see that we have one transmitter which has 2 lasers and 1 receiver. So that means 2-dimensional Vx and Vy could be seen from here. So now this result is the gist of the experiment. So we see velocity Vx and velocity Vy. Upper side is constant volume spray chamber in the ambient condition, that is unpressurized. The chamber pressure is unpressurized, ambient condition, and lower side we see that the engine condition. So the lower side is the graph in actual firing optical engine. So we can see the velocity. So we were talking about, I think yesterday, how much is the, somebody asked the question, how much is the error if you don't have the actual conditions in the constant volume spray chamber. Did you do the error analysis? And this is the exact thing that is happening. So we see that the velocity is going in the, people have reported like 40 or 60 meter per second in the constant volume spray chamber. But when the droplet experiences different high temperature and high pressure environment condition inside the engine, the phenomena changes all of a sudden. So the velocity drops. The velocity drops. There is no head section in the beginning. It's almost very small, and each droplet here depicts the individual droplet that is coming out of the injector. So this is velocity, and similarly the other direction velocity in the Vy direction. So that also decreases. And if we see this, this is a joint PDF. That means the density of the droplet at particular time and a particular velocity. Okay, I don't have droplet. I could not put droplet size, but the droplet size also decreases. Yeah, we can see. Look at here. The droplet size. This graph is here. The droplet size, the solder mean diameter for the engine condition, we are here, and for the constant volume spray chamber, we are here. So we talk about that the inside the combustion chamber, when the droplet experiences high pressure and high temperature condition, the droplet size is different. It is smaller, and when we talk about the physical significance of this lies in the fact that the droplet size, we calculate volume of the droplet that is required for the mass and heat transfer. So it is cubic time. So this is cubic time. That is how you can interpret these results. The droplet size, even if it is 4 microns smaller, then you can cube that. So that is the difference. And here is the velocity. If we take an average at certain time, the duration, and then plot a single line of the previous graph which I showed. So this is constant volume spray chamber. The velocity is going all the way from 60 meter per second, and then at the similar condition it is lower, 15 meter per second. So this is the difference between the two conditions that we usually see in the literature. Okay, then with this understanding, we have gathered the understanding of the ambient condition and optical condition. So the second part of the presentation is focused on the particulate emission sites. So with this understanding, we have focused on the measurement of the morphology. Morphology here means the particulate size, individual primary particle diameter size. How does that affects with these conditions? So this is the TEM images. TEM image has been taken. First we collect the soot in a controlled condition, and then we perform load the soot sample on the on this TEM grid, and then TEM grid is taken to for the investigation. These images has been captured. So we see that the images, from these images we have certain, the soot has certain curvatures inside. So these are typical shapes of the low curvature, medium curvature and high curvature. And what does this curvature say? Maybe this tells us about the soot reactivity and soot oxidation characteristics, and this is widely available in the literature. I have also taken from the literature. So when we get the images, we need to convert those images from the raw to the binary images, and then from raw to the binary image we can see some curvatures in the different direction. For example, you see here, so the curvatures can be in either of these shapes, and these shapes may decide the soot oxidation and soot reactivity conditions. So there is a methodology how we move from that to this side, but I am skipping that methodology. And also this soot has a tendency to either agglomerate in the direction of a sphere, or has a straight line agglomeration. So with this, the image is little bit blurred, but this soot can be agglomerated. This agglomeration can be further characterized with respect to skeleton length, skeleton width, and this can be correlated. It is very difficult to say very precisely that this may be the probable reason, but that is how we did to calculate the core diameter of the individual droplet or the skeleton length or the skeleton width of the soot particles. And then we can also have this diameter. So diameter from this morphological one, and this is from the DMS 500 particle number size distribution. So here we see that the peak is around let us say 100 micron, but here when we do the morphological analysis, so we get peak around 35-40 microns of the primary particle diameter. So here also there is a difference that is reported. So this is from the soot collected in a filter paper, that 47 mm quartz filter paper, and this one is from the gas that is coming out from the tailpipe, and we try to measure that the soot number size distribution, and that is the methodology to calculate the primary diameter. And this is another experiment from this soot. Everything is same, but here we use either a catalytic stripper or we use a thermal denuder to strip off the molar particles, and we have this photoacoustic soot spectrometer to see the behavior of the particles. So what is the study that has been done in this is, so we have a particulate filter. We try to measure the particulate upstream and downstream of the filter. So upstream and downstream of the filter with UV lights turned on and off, and the UV lights are 405 and 781 nanometers. So we see that on the lower side, this will have a lot of error because the inherent the instruments, they may not be able to they may not, although the OEM says that they can measure a smaller size, but there may be certain errors in this, but we can see this difference in this. The soot, when it comes out of the filter, that is on the downstream of the filter, upstream of the on the downstream of the filter. So we can see on the downstream of the filter. So this soot on the downstream of the filter. So we were aiming to see this particle number size distribution on the downstream of the filter with these UV lights. And these particles, when they come out of the diesel particle filters, are still have certain size, and that is also the people can inhale. So I am not able to. I don't have much of this result at present, but that was the investigation. Thank you. So this study, I would like to tell that this study was done at Chalmers University, Sweden, and it took about 1 year to set up this setup, and all this study was done. This one is at IIT Kanpur, and similar study was done at Chalmers, but all these results was done at IIT Kanpur with all the constant volume spray chamber and optical engine results during my PhD, and the other results are from my postdoc work. Thank you.
So actually you have mentioned about low curvature, medium curvature and high curvature soot.
This one.
So do we have something in literature about the diesel, that in diesel which type of basically soot particles are more? Do we have high curvature soot and which are good for the oxidation?
So it is very difficult to say for me at this stage, but first of all, these curvatures are maybe same for diesel engine and gasoline engine soot particles. Diesel and in gasoline engine we don't have soot because the phenomena is port fuel injection. This is for the direct injection.
I'm asking about basically if we have like diesel and if we have any biodiesel, do we have difference in the low curvature, medium curvature and high curvature?
Yes, there is a difference.
And which one are good for the oxidation? Is there any study available on this?
There are many people, science background, they have done this study, but it is difficult for me to tell at this stage. But this curvature you can predict this, you can say something about the soot oxidation characteristics from these curvatures. And how do you measure this? There is a certain threshold limit when you measure when you measure this skeletal length and skeletal width. So you will have different length and width, and then at a certain point we make a cutoff of this, that if this is beyond this, we can say it is more inclined towards the soot oxidation. So this type of studies have been done after measurement, because when you measure you cannot say anything about the soot reactivity or soot oxidation characteristics. So we need to make a cutoff at certain point, and I don't remember that cutoff. It may be 0.5 or 0.4 something, and that is the ratio.
In one of the cases you have shown.
Yeah, so I think can you show the next slide?
So this one?
Yeah, so it is impossible for anybody to tell.
Yeah, it is not very difficult.
Which, if you look at that Venn diagram, for example,
Yes, sir.
you are talking of a nanoscale. So these are almost like carbon atoms. You are talking of nanoscale. Look at the scale. So this is how the carbon atoms are organized. So when you have a soot from diesel or biodiesel, you will have low curvature, you will also have medium curvature, you will have high curvature. It's very difficult to quantify how much is what. And it is almost impossible to predict that, if you change the fuel composition, then you will have a soot which can be oxidized. It's right now it is almost a state of the art science. This is where we are. So very little understood beyond it.
Yeah. So what you can at max say is the shape is like onion shape structure, or the orientation is like this. The pattern like we have on our fingers, or something like this. You can find it in different soot images. You can find these patterns, different types of patterns. Yeah.
And this is like oversimplification. This is not, the patterns that he is showing, not exactly that you will have circles of fingers.
Yeah.
But that's what you try to
Yeah. For example, here, so we see that maybe this has certain curvature. It's going like this. It's not very clear, but on the exact images it will be like, you can see the onion-like structures or something. But you cannot say anything with for sure that this may be this is like this, so maybe it is like this. So it is not. You cannot say anything from these.
Actually, this is new for me. That's why I was
But
curious.
you are sure that the graphene-like structures are there?
Yeah, it's widely reported, not by me, by many of there are many people, those who work on this soot images. So it matters that how do you take the images. So there are two types of 10 grids. So one is lacy 10 grid, and another one is, I don't remember, but there are two types. So this one is, if I would have done this in the lacy 10 grid, so these images would have been more better for this type of structure. But I have done for the calculation of the primary particle diameter. So for that that 10 grid is more suitable, and we can have this type of measurement of the primary particle diameter, and we know that wherever the peak lies, maybe that kind of study can only the primary particle diameter and the location of the soot particles and how they are agglomerated. These kind of things you can interpret.
Yeah, why I am asking, because there were a lot of reports where it is found that soot is amorphous.
Yeah.
Okay, so when you were talking about this thing, definitely you have got it
Soot
from
is,
some literature.
Yeah.
So if they check the despacing of these lamellas, whether those are really graphenes or not.
Yeah, so you mean to see the spacing between?
Yeah.
Yeah, so we also try to do this. So spacing also people have calculated, and it is very intense, as I told you here. So they measure this length also, skeletal length L, skeletal width W, and then LSK and WSK, and they try to have certain cutoff and say that if this cutoff is there, the agglomeration are in a chain-like structure. And if this cutoff is beyond this, and it is like a spherical-like structure.
So
These kind of
agglomerated shape will depend on that.
Yeah, and when you say about the distance between these two layers, so this is widely available in the literature, and this you can calculate using commercially open source codes also, like ImageJ software. You have certain threshold value on those images, and correct those images for threshold, and then you can calculate either by manually or with MATLAB code. But manually it will be more better, because in the MATLAB code the code may not be able to distinguish between the white and grey structures because they are very close to each other.
I have a
But
question
again,
on the particle
just one point
diameter.
in this. The XRD also will give the
Yeah,
whether
XRD
it is, that is the best
XRD
for amorphous or this.
are not included because of the time limitation.
But
we
that
can do
gives an indication whether
Indications,
amorphous
yes.
or
But
Exactly, the limitation is that it's a point measurement. It doesn't give you an actual representation of the average area. Point measurement, that's the limit.
it is amorphous in nature. That what you can.
standard practice is not XRD in case of suit.
And the TEM also gives you the images give you the nature of the soot particle, and it is amorphous in nature. That's what it says most of the time. Yes, sir.
Yeah, my question is, one, you have used the in situ soot particle diameter concentration measurements, which is shown on the right hand side. On the left side, you told that it is based on the soot which is collected on the filter paper, and then the morphology based this one.
Yeah.
So for both the cases, the dilution conditions are almost same.
So the yes, so we have a certain protocol to follow when we measure. The dilution ratio has to be maintained equal, same.
So in that case, see, if we compare both the conditions, the sampling conditions, in this case it must be at a higher temperature, the exhaust gas after dilution,
Yes, yes.
compared to this morphology, because this is where you are collecting in the filter paper
Yeah, and then we process.
and then we
that.
are processing. So typically when the temperature goes down, more of agglomeration and the size should go up, right? So if you compare on the right hand side, the size is higher, but on the left hand side, the size is lower.
Yes, this is lower because of the many things. We cannot know why it is like this, but this may have the soot particle may have a hydrocarbon deposited on the periphery of the soot particles, and that may increase the soot size also. And these, how they are tuned, how they are calibrated, this SMPS and DMS also depends on that. And when we say about dilution, and then we convert that dilution back into the real, multiply by the dilution factor also, and that is the difference.
Okay.
If you measure this by DMS 500 and SMPS 500 at the same time with two different probes, you will find a difference in these also. The peak may be shifted to certain the lower side or the higher side. Then it may be, most of the time it is around like 80 microns or something, and this will be like 30, 35, 40 microns on this side.
Thank you.
Because of the nature of the gas and the different phenomena that in the tailpipe there are many hydrocarbons, and they are with respect to high temperature they are converting from one form to another as they travel the distance, let us say 3 meters. So we don't know what phenomena is leading to these two differences.
Yeah, so under this figure and the comparison of you are comparing the soot particle diameter of diesel and renewable fuels, right? It seems like with renewable fuels the soot renovation process is less.
With respect to
Diesel.
yeah, so after analyzing these I may have these here. So renewable fuels and the diameter. Yeah, so diameter peak is shifting towards the smaller size for the renewable fuel. Slightly, it is not that, but we can see the peak is around here, and from here the peak is at this side. So for the renewable fuels, the diameter is decreasing. Maybe the reason may be that the renewable fuel has oxygen content in that, and that may lead to the smaller in the size of the droplet, of the soot particle.
Basically, increases the oxidation process.
Yes.
Thank you again.
Thank you.
Long live India and France friendship.